Olele, olala, everybody. We are going to jump right in. So here we go. Today, we're obviously in geometry. We are going to begin looking at chapter 3. And I don't intend on us having homework today. Just a heads up. We won't have homework. We'll have time to work on stuff tomorrow, but we're going to build all of our intuition, which, if I say this, maybe it makes it true, but we do have a bit of front loading to do today. So in chapter 3, our entire focus will be on transformations. Okay. For this, I would recommend, if you want to write the word transformations, that is completely fine. I like to call them transforms, because we have done transformations in algebra. Yep. Okay. Very different. Like, same ideas, but different lens. Okay. So, right off the bat, 3.1, I'm going to hold off on naming it. It does have a particular name, but we'll come back. I don't want to spoil it yet. Can you guys guess what sort of transformation we're looking at?
The one that we just did, the symmetry.
Symmetry. Was the symmetry we just saw from a reflection or rotation?
Reflection.
Okay, so I guess I don't have to hide it. We're talking reflections today. Okay. Now, as we look at stuff, we're going to be able to find reflections both on paper. If I just give you a flat surface with a picture, we can reflect it over something, but we're also going to be able to do it on the coordinate plane. So we will tie this back to algebra stuff, at least a little bit. To start us off, our first main topic, it's going to be fairly short, but we're going to define for ourselves rigid motion. Now, right here, I'm going to pause. What is rigid? What does that mean?
Like
So I hear a few different things. I hear bumpy, and I heard sharp first hour, and I've heard sharp year after year. And if you think sharp, I get where you're coming from, because you might be thinking about the ridge of like a mountain, where it comes up like this, and it's like a sharp edge, right? Okay, that is ridge with a D before the G. This is a different word. Rigid. What was yours, Michelle? Not flexible or stiff, not changing. A metal pole is rigid because you can't bend it. So as we're looking at this, we're going to look at rigid motion, and we're going to define it. And with the understanding that your book uses motion, I think it's a fair thing to use. I like to call them rigid transforms instead. And I'm going to write that here, transform. Now, I will never put this on a question anywhere or use the word outside, but there is a real word for this. A rigid transform, if you want the fancy math word, completely optional. I want you to know that it's a transform and that it's motion, but completely optional. So only if you want it. This is formally known as what is an isometry. An isometry is the real fancy math word for a rigid transform. Okay. Now, as we look at this, super easy to define, and I'm going to kind of piggyback off what Michelle said. She said, one more time. Not flexible, not changing. And I'm just going to make that a little bit, I guess that's really concise, but I'm going to be a little bit more wordy than that. We're going to say no changes to only two things. We can't change or make changes to lengths or to angles. Now, with that said, there's several different types of these rigid motions or isometries that one could encounter. Okay, you guys have already hit one of them, and it was pretty obvious. A reflection is a type of rigid transform. And it's weird when we look at three-dimensional figures because it doesn't really work, but check it out. Here is my hand, right? If I reflect it over this line, forget about that our hands have features, we're just looking at the shape. If I reflect it over this line, do I get the same size, same shape? Like when I go over this and I reflect it, I get the same, even though I know we're looking at the front and back. Yeah. Nothing changed, right? Still the same size, same shape. How do I take my hand here and go, whoop? I did rotate it. Did I change? I changed the way it was oriented, but it's size or shape. Like my hand's still the same size, right? My fingers probably move a little bit just because anatomy, but it's the same general size and shape. Okay, there's one more.
Slide.
Ooh, I like the word dilation, but I don't know that I like it in this context. A slide. There is a more formal word. I literally just had a stylus.
Translate?
It is translate. Maybe see where I put my stylus? Oh, right there. Cool. So we have reflection, we have rotation, and we had translate, which that's our slide if you like the more informal language. Okay, these are the only three that can be counted as a rigid motion or an isometry, a rigid transform. Now, Liam said something else, and I'm going to ask a question that always makes people think I'm a weirdo. Not really, I'm making it up. Have you guys ever looked in the mirror? You ever looked in the mirror in your bathroom?
No.
Have you ever,
Never seen it.
have you ever looked in the mirror in your bathroom and had the light switch right here and turned it off and on and looked at your face?
Yeah.
Okay, if we zoom in a little bit, if you don't just look at your face, what might you be
Shadows.
looking at? The eyes. Why would you care about what your eyes are doing as you're standing like a weirdo and
Dilate.
doing this? Your pupils dilate. How many of you guys have seen pupils dilate before? Okay, if you've never seen it, it's crazy. I'll use mine. I wish you all had phones, but I'm not going to use phones. Okay, same thing. We could, like, if somebody has a possible concussion, they're going to run up and the doctors are probably going to do this. They're going to open their eyes and do this. Because if they have a traumatic brain injury, maybe their brain reflexes don't work. Our pupils change size constantly. All the time they're changing. In the dark, are pupils big or small?
Big.
Why?
See better.
The bigger that hole is, and it's literally a hole in your eye, the bigger the hole is, the more light comes in. The brighter it is, the less that comes in, right? So if you're into photography, if you've ever changed the aperture on your setting, you're doing the same thing that our eyes do naturally. Somebody over here said they've never seen it. You've never seen it? Okay, so check it out. You see my pupil? Okay, pupil, see right now how big it is? You see it physically changing size.
You gotta zoom in.
We might have to turn in the light. We'll turn off the light. I'll record a video of it. Okay, or better than that, you guys just go home and be. Yeah. I can, yes. Okay, we're gonna look at these, just rigid motions. And this one's gonna be obvious. This is not so much as an example as just a demonstration of here's this fact. Okay, I'm going to draw this better than you guys are for a very particular reason. Now, let's say we start with this triangle. And notice it's just on a plane, right? There's no ordered pairs, there's nothing. I'm going to take this and I'm going to make one of these three rigid motions. And it is going to be very obvious which one I make. I'll verify that. But let's say this is the original place that we're starting. And we're going to do some sort of transformation to this. In your notes, even if you don't want the picture, I do want you to roughly have the picture at least, because we're going to sneak in a little bit of vocab here. This is the original image that I'm about to transform somehow. Now, original is good. That's a fine word to use in just common language. Turns out, oftentimes in like every academic setting, we have specific words for stuff. Rather than the original, the formal way to refer to this is the pre-image. Okay, the pre-image. That's it. I don't really know if there's a hyphen in it, to be honest. I should double check that. What do you guys think? Is there a hyphen in that word? Nope, there is no, a dash. There is no hyphen. Okay, so it is going to be crazy obvious what happened with mine. Let's say I take this, and here it is, and I'll get rid of the EG part, but I can move this down to here, right? Like, it's a different location, bless you, but did I change anything about it? Other than its location? No. Now, something has happened. Was that a reflection, a rotation, or translation? Okay, so that was a translation. Now, when we talk about this, this is, for lack of a better term, my new picture, right? Here's my original, and here's where I wound up after some translation. Now, if this is the pre-image, this one, 2 guesses. Post-image, I heard somebody say, which is a really good thought. It's just our image. We have the image, which is found by changing the pre-image. Before the image and the image. Now, one other little piece that we're going to change, because if I had a bunch of these, I'm now going to have a bunch of different points that I labeled B. And I need a way to distinguish between the original B and a new value of B.
B1.
B1 is a great thought. It would work, and I'd be cool with it, but it's not the standard convention. Instead, we use these little apostrophes. So check it out. I've only done one single translation from here to here. I would call this A with an apostrophe, C with an apostrophe, and B with an apostrophe. Does anybody recall how we word these? All right, let's see here. No, I was going to make a dumb joke, but it's not worth it. This point right here is called B prime. This point here is what? C prime.
B prime, C prime.
This is A
Prime.
prime. Cool. Okay, now, later in the chapter, we will be doing more than one transformation at a time. If this was the first translation, and then I did another one, what do you think I would call the new point?
B.
B prime prime, which feels funky, double prime is how I say it. B double prime, or C double prime, or triple prime if we had 3 of them, so forth and so on. Okay, so looking at this is a rigid motion or not? Yes, this is a rigid translation is what we're seeing here. Now, if we wanted to, and I don't know that we need to, I'm just going to highlight here, this is a rigid transform, or motion if you'd rather. If I drew 2 triangles but one was way bigger, would that be rigid or non-rigid?
No, not rigid.
Non-rigid. Do I have to draw it?
No.
Okay. I'm cool with it. Now, we have at least this basis of getting rolling with stuff. So we're going to switch gears here. We are focusing, out of all of these today, our goal is reflections. So, real quick, Henning, what color is a reflection? So I'm going to write reflection here in a second. What color is a reflection? There actually is an answer to this, just so you know. There is an answer. Reflections are green. Mirrors give off a slight change in the color of the light. It's a little bit green. You don't notice it, but mirrors are green. So I'm going to use green. So I'm not saying they're made out of green, just for the record. Green. Green. There's a slight hint of green, whether our eyes perceive it or not, because the way that when light loses a little energy, it changes wavelength, which changes the color. Really bright. There's YouTube that. You'll find an answer. All right. So here we go. Reflections. As we look at these, there are a few different ways to think about this. Now, I'm going to take the very mathematical and probably kind of algebraic approach to this. When we think of a reflection, we're going to use very specific language. We're going to think of these as being a mapping. A mapping. And we'll clean up what that means. A mapping that moves each point in the preimage, each point in the preimage to a new point on the image. Okay. There's more to this, but we're going to pause there. In general, it's just a mapping. It says, hey, here's point A, and it was mapped or moved to point A prime. Now, between any 2 points, there's infinitely many, but luckily we don't have to do it for all infinity of them. Okay, beyond this, first thing, I move from preimage to image. That's the first part. Every single point has to be moved. Beyond that, though, we're going to say such that, and I would encourage ST, because that's going to start showing up more and more, such that the perpendicular distance, and I'm going to use that new prime notation here, from A or A prime to our line of reflection, to the line of reflection, is equal. Now, this is the wordiest definition, I hope, that I'll give you all year long. A mapping that takes each point from the preimage to the image in such a way that the perpendicular distance is the same from that line of reflection. Okay. We're going to make sense of this, and we're going to do it in 2 different ways. Before we move to the coordinate plane, which I'll give you guys graph paper and stuff while we do that, because it turns out if we look at this with algebra, these things get a little bit easier. But we do also want to try to do it on just the flat plane without ordered pairs. Okay. This mapping thing will show up. There's a very specific notation that I've never seen another book use, but I use it, and I think that it makes stuff easier, seemingly. Cool. All right. So let's knock one out. Let's look at an example of this. And here's what I want us to do. I want you to reflect AB over, and we'll say it line L. And here's the cool part. Because there's no ordered pairs or anything, we don't have to be like crazy specific. Now, I'm going to be really judgy about this. And I'm going to wait. Do I need to pause for a second because I'm already going fast? Yep, I'll pass them out here in a minute. But we don't need it for this one. Okay, check it out. Let's make a segment AB. And I don't care what it looks like. We'll say it's this. And I'll say here's point A and here's point B. Now, if you don't have a straight edge on you at this point in time, you should stand up and walk back and grab one out of calculator slot number 2. You should use a straight edge, specifically a protractor.
I'm surprised I found a green head in my bag.
A green pen.
All right. And people are getting them. If you want to keep it, you can. If you want to put it back in number 30 on your way out, totally fine. You're not going to need it tonight. Okay. Here's what I want you guys to do. On your page, you're going to draw a line. And notice, all I care is that it's a straight line, which all lines should be. Here's my line L on mine. And I'm going to do the same thing on paper, but here's my challenge for you. I want to see where you guys are at just initially. So my challenge, and I'll pause the video and I'll come walk around. I'll do the same thing on a piece of paper so we can look at it. I want you using your compass, your protractor, which has lengths included. I want you to reflect over line L to find me A prime, B prime.
Like exactly? Like,
Yep, I want to see where it is. Now,
is it method?
what's up?
Alright, go ahead.
I should be able to, and I hate grading these because of this, but when I grade these on quizzes and tests, it takes forever because I physically measure stuff, and it sucks. But I just want to see how in-depth we have to be with use on the protractor. Your job right now is to find me B prime and A prime, and then connect them. Cool. I'll come around and be really judgy. Cool.
Oh, so we have to measure?
I'm not going to give you any other guidance. You should measure something, for sure. But I'll give you a minute. Okay. So as I'm looking at my protractor, I don't need to measure angles. And really, I don't have to super measure distance either. Do you guys notice on your protractors, right at this circle, there is a straight line through? Now, if I extended it up, that straight line, gentlemen, you should be watching this because you'll use it. It lines up with 90. Similarly, these lines that run horizontally, they happen to line up with 180 or 0, depending on where we're looking. When you're using these, here's my suggestion, and what's going to make it easiest. I think that I can reasonably well line up the black line right here that runs right through the middle with my line. Okay, everybody agree that it's not perfect, but it's pretty good. Now, on mine, if I wanted to have it better, I could extend this up, and I can make sure I see that third line so I get straighter still. But here's, for all intent and purpose, where I'm at. Okay, if it's lined up, and it looks pretty close, I know that this is 1 centimeter. Now, it's zoomed way in, so that's actually like many centimeters. But notice, they're in tenths, which is how the metric system works. I think on my picture, I see 1.1 centimeters. Do you guys agree?
Yep.
Now, when we talked and wrote down that perpendicular part, whether you were aware of what was really going on or not, I can see that everybody had the same basic idea. And I think you would have if I hadn't said it. If instead of being here, I needed to keep that distance the same. I know that point B prime will be over here. Is it going to be here?
No.
No, I should go how far from this?
1.1.
1.1, about the same, right? So I put that there, and I will label that. What's a good name for this new point?
B prime.
B prime. Don't forget that. No, okay. All right. I was trying to make a joke telling you to keep being prime, but you're good. Okay. On B, we can do the same thing. Now, or on A rather. Now on this one, I don't have to extend my line, but I now have 2 points that are much further away. All I'm going to do is line up my protractor so that the very bottom of it is on that point. Do these lines look straight to you? All the way through?
Yeah.
Okay, so let's see. I'm 2.1 centimeters? 2 you say 2.2? Maybe. 2.1, 2.2, somewhere in there. So I'll split the difference. 2.1, 2.2, I don't know, somewhere in there. There it is. What should I call this? A prime. Now, when we connect them,
Why should you just not go opposite direction?
it does. Up to the left, or up from the left.
For some reason when I see
Okay.
it, it looked like
Yep, so it was just tilted like that. Now, common issues here. And I think that whether we talk about it explicitly or not, you guys all did it, but we are going to talk about it explicitly. As I look at this, if I said, what's the distance from B to this line, and I gave you all the exact same picture, are we all going to come up with the same number? We should. However, if we don't say perpendicular, it is completely reasonable to expect that somebody does something wonky. If I said measure the distance from this point to this line, and somebody said, oh yeah, Holloway, I got you. From B to the line is 4 centimeters.
What?
Sorry, there you go. 4 centimeters. That's the distance, right?
These measure straight across, right?
They're not wrong. Would you agree?
They are wrong.
It feels wrong, but just with that, they're not truly wrong. Now, when we measure, it makes more sense to let's all agree to measure the same every time, right?
Yeah.
I think that we're using naturally that perpendicular idea to measure that distance. Okay, it shows up. This method, if we connect these, and you don't have to connect it like hardcore, but I'm going to try to draw my line really light, and I'll actually just use a colored line here. If I connect these, and I just connect them straight through, what I notice is a couple things. One, I have a segment, but if I put a point here, it's like I have 2 new segments, right? This distance had better be the same as this distance. If I put a point here, and I went straight through, this segment would be the exact same as this segment on the other side. Now, I'm only going to highlight a couple of them, because we don't have time to do all infinity of these points, but every single point between here does exactly this. If I were to measure, I'd see this is congruent to this, and we could do it for infinitely many points. Okay,
Just connecting all these.
so I don't really have to connect them, and you don't really truly have to do this. I just want to really point out that this segment must be the same length as this segment, and more so that we measure it perpendicularly. Every time we measure perpendicularly. Okay, I saw a few people in both of my classes of geometry do translations instead, and I totally agree. Like, it's easy to get goofed up. If you had issues, does it feel okay now? Let me rephrase it. Does this feel not okay for anybody? Everybody seems okay with it? Okay, here's another challenge for you then. We're going to do this one on paper. That was example A, right?
Yeah.
Okay, I want you to do B, and I want you to draw a triangle for me. I would try to make it not equilateral, so different side lengths. I would try so that it's easier to pick out. But let's draw a triangle, name it A, B, C. I don't care what yours looks like. Here's mine. And your triangle might look very different, but that's okay. All I need from you, really and truly, is a triangle on your page. Yep, you have a triangle, perfect. Okay, yours is equilateral, so it might be kind of hard to tell. You're okay. Label your points. Label your points A, B, and C. Don't care what order that happens in. Now, on this one, I am not going to require it, but I strongly recommend whatever you use to draw, you guys are obviously all going to use the same pencil. I would do something different when I make the image. So if this is my pre-image, when you do the reflection, you could either use dash lines to try to indicate that look at the difference in shapes. You could grab one of these wonderful colored pencils if you would prefer to do that. Some way to tell them apart more than just the points, because I'm about to make this, I don't want to say bad, but everybody has a triangle? All right, we're going to add a line, L, and we're going to reflect over it. And here's the only rule. I want L to go through your triangle. Here's the line L that I'm going to reflect over.
Oh, what?
Yep, we're reflecting over that. And I want you guys to try that for me. We'll come back together in a moment, but I'm going to come around and be really judgy for a second time. Cool. Try to reflect this. You're using your protractor. If you hear me say that and go, what's a protractor? I have no idea what to do. Don't just sit there and wait for it. Don't eyeball it. Let me show you, because again, on quizzes and tests, it sucks from my end, but I physically measure stuff. Cool. I'll give you a minute, reflect it, and we'll see if we get the same picture.
Oh, I know.
All right, so here I am. I'm doing the same thing. You guys all did much better. I did not go over the first one like we did just now in third hour, and when I told people to reflect this one, I got wonky shapes. I didn't see any crazy wonky ones here, so good on you guys. So I'll line it up. Looks pretty good to me. How many centimeters away from 5 does this look to be?
1.5.
1.5.6. So here's 1.5.6. It's about there. What am I going to name this new point that I just found?
C prime.
This is now my point C prime. Okay, I will do the same thing with point B and on mine, and all of our numbers are different, so please don't just use my numbers. How far away? 1.1-ish. Okay, so here's 1.1-ish. What is that point called?
B prime.
B prime. And finally, we'll do A. And I'm sorry to just make you watch me do this, but I was walking around. I see, I don't know, 1.75-ish. 1.6, 1.7. Okay. There it is. And check it out. There's my point. What? Sorry.
A prime.
A prime. Now, the last little thing. And if you only used pencil and you use solid lines for all of them, you can probably start to see why I'm suggesting we use either colored pencils or a different notation, something. Because even when I look at Sevilla's, who used only a black pencil, I can still tell the difference. Those look like reflections to me. Now, I can tell I'm not perfect because I think that this point that was already on the line should have landed back on itself. I was pretty close. Okay. These ones feel all right, feel awful.
Pretty good.
Okay. We're going to switch gears just a little bit. Yo.
Is this one good then? Because right here it doesn't really.
You're close. You can feel it better. Okay. I'm going to give you guys some graphs, paper, sticky notes. Just so you know, we're doing 2 examples. I want you to have 2 examples on this. So we're going to use the same picture. We're going to draw 3 of some shape. Cool. I'll specify these shapes.
C prime.
Thank you, Greg.
I think it looks like the little thing going on the little apps on the guy. Oh, wow. I kind of thought it was for a second.
I don't even know the pop.
It is sticky. Stick it in your notes.
Get in my notes. I only heard it from I didn't hear the actual. I forgot it now. So these are what you hear.
Okay. So, if you have graph paper, or if you need graph paper and I missed you somehow, did I get everybody? Jonah, I missed you. Could use graph paper for you. Jonah.
I didn't do that.
All right. So, for our next one, we're going to start bridging the gap between geometry and algebra. I'm just going to eyeball this one. I use it on paper. Now, I think I can eyeball it pretty well. Does that look perfect to you guys?
No, that's pretty good.
It's pretty good, but if I go to measure it and it's just pretty good, am I going to give you the point? No. I hate the measuring part, but it looks okay. It looks close.
Wait, if we get really, really close.
Yeah, I hate grading this chapter test. I hate it.
If we get really, really close, like if we're like a centimeter off, maybe like.
A centimeter is way too much.
Or like the I don't know which one's this one.
All right. I'm fair. I won't deduct it. I'm fair. Okay. So check it out. We have one more example that we're going to get set up right now. We're going to stick it in our notes, and that's where we're going to end. We won't even do the full example. Okay. We have done reflections, and we did a couple of them just now kind of floating out in the plane. Some plane. Somewhere. We're going to work on a very specific plane right now. So we're still talking about reflections, of course, but let's talk about reflections and the coordinate plane. What's up? I would put this in, so I would save the graph paper. We're going to do our example on the graph paper. That was not super clear. I wouldn't necessarily write this part on your graph paper. I would say the example is the one we're doing on the graph paper. That could have been more clear. Okay, now, we are going to work out some rules here, but immediately, you're going to use that graph paper to help make sense of our first example. Okay, we're going to look at this mapping notation, and we're really going to clean it up because we haven't even really talked about what that is. Today, here in just a second, you will be reflecting the same triangle twice. What's up? I am. Thank you for checking. Okay, so here we go. I'm going to give you triangle ABC. So I would draw the triangles on the sticky note. This part you can just write. Anybody else want to ask? Yeah, we'll write this part in our notes and we'll draw the triangle on the sticky note. Okay, so check it out. I'm going to do this in a very specific way, and it's going to look different than your book, but I promise it'll help. Triangle ABC, I'm going to give you some points. We're going to say that, and I want you to write it exactly like I am. A is at the ordered pair, -5, 6. Underneath this, exactly like this, I want you to say that B is the ordered pair, 1, -2. And then one more directly underneath of it for the last time. C is going to be the point -3, -4. Now, second thing, we're going to do this problem and we're going to see a couple different ways. I would leave all this space right here blank because when we talk about the mapping, we're going to see it happening. When tomorrow at the start of class, we'll work on this problem, but we are going to go from point A and we're going to end up at point A prime. We're going to go from B and we're going to end up where? At B prime. And we're going to go from C and we'll end up at C prime.
Wouldn't it be just the same thing? Just like opposite? Like, wouldn't it be +5, -6 then?
It depends on where we're reflecting, but I like that idea. All right, later Raiders, we'll go over the test and continue with these tomorrow. We'll specify. We haven't said